Hello. In this video, we shall be discussing further about the optical instruments, starting with the compound microscope. As the name suggests, it consists of compound lenses, means it's a compounded structure. So, compound formed out of, in this case, two lenses. So, compound microscope. As I said, it consists of two lenses, one near the eye of the observer called as the eyepiece, and the other close to the object which is to be observed, which is known as the objective. Now, let me draw the objective first. The objective is relatively smaller than that of the eyepiece in this case. Why in this case? Because in telescopes we are going to have a large sized objective and smaller eyepiece. Now the objective over here is relatively small, so here's a convex lens that we are using as the objective, and the object to be observed is placed well beyond the focal length of this so as to obtain a real image. The reason why I'm extending the principal axis that much, because I will be drawing another lens, but that is for later. So suppose I have the focus over here, and on either side I'll be having the focus at the same distance. So in my approximation the other one will be there probably, and here a really small microscopic object that is to be observed, that is placed in front of the objective. I'm naming it as O. The optical center over here is O1. So the light ray that will be emanated from the tip of the object, first one going parallel to the principal axis, is refracted through the focus as we know it. So that gets refracted through the focus, and till that point, and then I have another ray which is going to pass through the optical center, and that will meet the other ray, forming the image of the tip. uh, Spare me for the curved line, I'm not using a ruler to draw it, so almost I've tried to make it straight as possible, but mind you, when you are drawing ray diagrams, you should not risk it like this, especially from the exam point of view, and you must not miss the arrows and no double lines in that case, so that you score well. So in this case you have the image over here, and it's a real one, and what we have is another lens, relatively greater, larger in size, and there's the optical center of the lens, uh, O2 we call it, and that's the eyepiece where the observer is placing his eye behind the eyepiece to observe the image. Now, as we know that the image, for being distinctly visible to us at the near point, must be at the least distance of distinct vision. So what happens is that the rays which actually are considered to be emanated from the image, from the real image, they get refracted, and then they are produced backward, just like in the case of simple microscope, because they will be this image that has been obtained. Let me name the object and the image. So the object here is AB, whose image is supposedly A1B1, and the points, the from the tip of the image, this A1B1, that lies within the focal length of the eyepiece, and that is why the refraction here follows the case of refraction through a simple microscope, where the light ray is emanated from the tip. Let me take a light ray over here passing through the optical center undeviated, and what I'll do is I'll do a bit of manipulation actually, so that I get a clearer image. This is just for obtaining the image from the diagram point of view. Nothing really wrong with that. small manipulation that I'm going to do. What I'm going to do is I'm actually going to set the point where I'm supposed to get the image. Let that point be over somewhere over here. And so I'm saying that the image is probably obtained over here. This is the least distance of distinct vision with respect to the given eyepiece. And actually what happens is that now I'm going to extend those dashed lines up to those two rays which are there. And then I'm going to extend it further on this side. What I've actually done is that I've taken it the other way around. This is the eye of the observer who is observing it. And what happens is that the light rays, after getting refracted, these rays that we have over here, these rays actually get refracted, they diverge to that extent that I have shown, and when produced backward, they form an image that I have shown over here. And that image, let me name it as A2B2. So that image that is formed over there, uh, that should have been the case where the light rays, after diverging onto the other side, are produced backward to meet at that point. But what I actually did, as you saw, is that I first drew the image and then I produced the light rays in the forward direction. This is just a manipulation that I tried to form the image. What actually happens is that, as I said, the rays get diverged and they are produced backward. Now, if I had gone the other way round, that is, I would have diverged them and then I would have tried to meet them in the backward direction, then they might have not met at a desired point within your answer sheet or within your paper, so you wouldn't have been able to show the image formation clearly. So this small manipulation is acceptable at this stage. Now, what we know is from our case of magnification in simple microscope that we tried in the other video, previous video, we have the angle subtended by the image to the angle subtended by the object. Now, the angle subtended by the image, as I'll be showing by the red mark over there, is theta I, and because that's the angle subtended by A2B2, which is the final image, and that is at the least distance of distinct vision. Now, what I must consider is that the object must be also placed at that point so that we are able to compare. So I consider the object to be in the form of CB2 to be present at the least distance of distinct vision, and that would subtend a certain angle which I take as theta O, that is the angle subtended by the object. Now, with the angle subtended by the object and that by the image available to us, we can now determine the magnifying power of the compound microscope. So the magnifying power of the compound microscope, as far as definition goes, is the ratio of the angle subtended by the image to that by the object. And because obviously you are dealing with very small objects, microscopic objects that you are going to visualize, the cells and the various things that you observe under the microscope in your laboratory, in the laboratory. So in that case, you have these angles being very small. Angles are small, and that is why they're small enough to be considered as tangent of theta I over tangent of theta O. And then you have the ratio of these tangents as well. For theta I, as you know, we have A2B2 over B2O2 in that triangle A2B2O2. And then in the denominator for tan theta O, we have CB2 over B2O2. Well, as you can see, the B2O2 can get cancelled out, and what we are left with is A2B2 over CB2. Again, we know that CB2 is equal to AB, so we have A2B2 over AB. This is exactly the way we tried deriving the magnifying power for simple microscope. Obviously, the conditions are a bit different. Now, A2 B2 over AB. Well, I can just write it as A2 B2 over A1 B1. I divide the A1 B1 factor and again I multiply it uh, over there. So A1 B1 gets multiplied and I have the AB present as well. Now, if you observe this, this is the magnification in case of the eyepiece, because the eyepiece is having A1 B1 as its object and A2 B2 as its image. So image size over object size is going to give me the magnification due to the eyepiece. And as we can also observe over here that the eyepiece is magnifying in the form of a simple microscope because the object is lying within the focal length. Now, if the eyepiece has a certain focal length given by f subscript e, and that of the objective is f subscript o, so we have this magnifying power for the eyepiece, which is A2B2 over A1B1, that can be given as that we have obtained for the simple microscope, that is 1 plus d over fe being its focal length, just I have defined it. So because the image is obtained at the near point. And then for A1 B1, what we know is that that is the image distance in case of the objective. So I take that as VO, which will be positive in terms of sign convention because that's on to the right hand side of the objective. And A1 and AB, as we know it, is the object distance UO, and that can be taken as negative. So this is negative of UO. So this is going to be the magnifying power in case of the compound microscope for the image obtained at the near point. So this is D, that is the near point. Now we also have the case where the image is obtained at the far point, that is at infinity. And as we know, and that is the normal adjustment that we do for image obtained at infinity, we have that is the far point, and that far point we have the magnifying power in case of the eyepiece that will now change to d over fe. Well, and the magnifying power in case of the objective remains as such. This one's for the eyepiece, this one's for the objective. Now, here also I can add that this is actually the magnifying power of the given compound microscope is actually the magnifying power of the eyepiece to that multiplied to the magnifying power of the objective. Now, what we also have, uh, we can consider. Now, let me write this as normal adjustment. Now, what we can also consider is that the the object, when it is placed at the focus of the objective, so AB, if placed at FO, that means you have UO, that is the object distance, to be equal to the focal length of the objective. Now, as you know very well that when an object is placed at the focus of a convex lens, the image is obtained at infinity. Now, in this case, infinity means the parallel rays to be moving along the collimated compound microscope. And what happens in that case is that the rays travel through the full length of the microscope. Now, the length of the microscope in this case that we usually consider is actually the distance between the two lenses. So if I'll write it above the title. So from the objective to the eyepiece, I take the length of the microscope, and the parallel rays are going to travel through the entire length of the microscope when the object is placed at the focal length of the objective. So we have V naught, instead of taking it at infinity, we have VO, that is the image distance, to be equal to L in this case. So now what we get is the uh, magnifying power from for the case of uh, image obtained at near point. We have the magnifying power under this condition as L over negative of FO. Now, although we know that the focal length of the convex lens is positive, but because the object is placed to the left, so by sign convention, we are considering the focal length, but the object distance is to the left, so negative of that. And that multiplied with 1 plus D over FE. Now, if this is considered for the normal adjustment, then for the normal adjustment, we have both the cases taken into account. So we have L over FO in negative, and then we also have a D over FE in case of the uh, eyepiece. So the magnifying power now becomes L times of D multiply over the product of the focal lengths of the objective and the eyepiece. An inverted image goes to show the meaning of negative sign in that case, so you can take it like that. So this is how we obtain the magnifying power of a compound microscope. As you can see over here, the magnifying power overall, you have an idea that the magnifying power is actually the product of the magnification or the magnifying power of the respective lenses. So the more the number of lenses used, the more is going to be the magnifying power. Usually we use for a basic level, we have two lenses employed in a compound microscope, and we can use more lenses. And also we know that the power of a lens, when two lenses, thin lenses, are separated through a distance d. I discussed in the 10th um, in the 10th video of this playlist that the magnifying that the power of the system of lenses in that case, where two lenses are kept in contact or they are separated through a distance d, we had obtained the power of the system. So you can refer to that as well. And in terms of the optical instruments that we use, this is the formula that we obtain. These are the formulas. So we have a few of them over here. That is, I'm using another ink to just show you the formulas that we have obtained so far. So that's one of them. This has been boxed. This has been boxed. We have another one over here. This is for the normal adjustment. And then we have the case of the object placed at the focal length of the objective. That's another one. And finally, for the case of the normal adjustment when the object is at the focal length of the objective. So all of these can be taken into consideration, depends on the case that we take into account at that point. So that's it from the case of compound microscope. In the next video, we shall be dealing about we shall be discussing the astronomical telescope, as well as the both the refracting and the reflecting type. And then we'll be ending with the optical instruments, and then we can continue to the case of wave optics. Till then, thank you for watching.